all of this really pushes hard on the question of how do we know the states in one dimension are not degenerate? Now, we had concluded this by looking at the videos of our solutions for the finite square well, that intuitively this really had to be the case, but it really does bear a more formal proof. Now, to prove that fact, I'm going to have to do the proof in two different stages. And the first thing that I'm going to prove was my original statement about the reality of the wave functions of bound states, that those wave functions always are just, if they're complex, they're just off by some constant that's irrelevant, reality of bound states. Now, I'm going to give a sort of non-standard proof of this. And the reason why I'd like to give this proof is that, well, first of all, as you will see, very quickly, once we've completed this proof, we will also quickly be able to prove the non-degeneracy, that there's only really, up to a normalization constant, of course, there's only really one solution for any given energy. And the other reason why I really like this proof is that it gives us good practice thinking about probabilities and probability currents, which was another major topic earlier on in the course. So to give us good practice with that as well. So let's think about this question of the reality of bound states. So let's suppose I'm given some bound state. Let's suppose phi n of x is a bound state. Now, it may or may not be complex. I don't want to make any assumptions. And so I'm going to write it in the form of its real and imaginary parts, right? So of the form phi n of x equals some real part, phi a of x, plus then I times its imaginary part, phi b of x. Right? Now, it may be that phi b is 0. I don't know. We are going to see. But let's just imagine the most general possible bound state solution for energy En, of course. Now, so we're going to suppose it's written in this form. What we're going to do is we're going to consider then, because as I had mentioned, I want to start thinking about probability currents, so I need to think about time evolution. Let's then consider the time evolution of this state, phi of x and t, and we know how this will evolve in time. It will keep its form in x, right? But then to that, we have to attach the corresponding complex exponential, e to the minus I, the energy of the state, which I said would be En over h bar times time t. So if that's my wave function, then when I look at the probability and how it behaves, something interesting comes out. So the probability density associated with the time evolution of this arbitrary bound state is the square of the wave function. So let me write that down, phi x plus I phi b of x, right, times e to the minus I En over h bar t, modulo squared. And of course, recall that the modulus of a product is the product of the moduli, so I can break this into a product of the moduli, but it was actually moduli squared, so this becomes squared. And then, of course, the modulus of a complex exponential is just 1. And that cancellation, though, tells us something very important, because look at this probability. Notice it has no time dependence left, so this is then constant with respect to time. And this is why such bound states, right, or eigenstates in general, but most often bound states, right, are often referred to as stationary states because none of their probability distributions evolve in time. Okay, so that's kind of interesting. Now, things get very interesting when I think about conservation of probability. Now, conservation of probability teaches us conservation of probability because the probability isn't evolving in time, we get this interesting result. So just in general, conservation of probability tells me that the time derivative of the probability density plus the spatial derivative of the current density, j of x in t, must always equal 0. But now that we know that the probability is constant with respect to time, that makes this term 0. But then that tells us that the current density must be constant with respect to x, because its x derivative is 0. So j of x and t is equal now to a constant with respect to position, x. Well, that's kind of an interesting fact, because after all, I'm looking at a bound state, right? And if the current density is constant with respect to x, that would imply it's constant even for very large values of x, far from my potential well. And it's a little hard to imagine how I could have a current density far away from my bound state. So let's take a look and investigate this. This must be telling us something very important. Now, in general, we know the formula for the current density. J of x and t has the following form. It's h bar on twice the mass times I, times then, we have two terms here. The first term looks a lot like the momentum calculation we would do for momentum. It's got psi star times the x derivative of psi. And then we subtract off kind of the opposite thing. We have the x derivative of psi star multiplying psi. And that's really, here I'll use square brackets on this, that's really my definition for the current density. Now there's something very interesting about this definition, because if we look at this term over here, I want you to notice that it is exactly the complex conjugate of the term that you see over here. Yes? Right? It looks like psi star times dx of psi starred. Because if I take this and I star it, the star on the psi gives me my psi back again, and then the star on the d by dx of psi gives me d by dx of psi star. So I'm in an interesting situation where I have a complex number minus its own complex conjugate. So just a quick side note, if I ever have z minus its complex conjugate, if I wrote z out as a complex number, a plus bi, and subtracted its complex conjugate, I would flip the sign on bi, right? What I get then, the a's cancel, and I get twice bi, right? Which is just 2i if you want, and b is nothing other than the imaginary part of z. So I get 2i times the imaginary part of z. Now, if on the other hand I were a little bit ambitious, I might divide everything through by twice I. Let's do that. Divide by 2 times I. This divides by 2 times I, right? And so I just get the imaginary part of z if I subtract it from its own complex conjugate and divide it by 2i. But look, lo and behold, very conveniently, there is a 2i right here in my expression, in my denominator. So when I combine all of this together, I get a very simple general result. It's a very beautiful shortcut for computing the current density. So I'm going to put a box around this just to emphasize it. Right? It's the imaginary part of this quantity, psi star times d by dx of psi. And let's put a nice box around this, because this is a completely general shortcut that you could use. It could be handy in all kinds of situations. Shortcut that works in general. Okay. But now back to our more concrete discussion. So for us then, I need to calculate the current density for this particular wave function. So it's h bar divided by m. Now I know it's the imaginary part of. The first thing I have to write down is psi, this is psi star. I'll make that look a little neater here. That is psi star. And psi, remember, was this function. So I have to complex conjugate this. So I'll get minus phi b and the positive time exponential for my psi star part. So that will be phi a of x plus I times phi. Oh, it's psi star, so it's minus I times phi b of x. And all of that multiplies my complex exponential, which is being complex conjugated, so it comes in as a plus I of En over h bar times t. And then this gets multiplied by the x derivative of psi. So I'll put that on the next line. This is getting a little bit messy. The x derivative and psi itself is phi a of x plus I times phi b of x times e to the minus I En over h bar t, right? And there's a closed parentheses there. Good. So now I can try to simplify this. The first thing I notice is that this factor is a constant with respect to x, so I can pull it out of the x derivative, and then it's just going to multiply with this complex exponential here. They have opposite signs, so just like with the probability density, the current density also happens to be constant with respect to time. So it's constant now, we know, not only with respect to time, but as we had seen previously, it's also constant with respect to position. This is really quite the constant. So let's continue evaluating it. We may learn something useful. So this is h bar on m. My job now is just to find the imaginary part of this product. So let's see here. I can see I get the terms that give me i's. I don't want any of the real parts. I only want terms that give me i's. The first term that gives me I is this first term times this second term. And the result of that will then be phi a of x, right, times then the x derivative of phi b. And I will just write that as phi b prime of x because phi b only depends on x. It, of course, also multiplies I, but I'm taking the imaginary part, so it's just this. Then I have one other term that is imaginary that comes from these two pieces. They come with a minus sign, so I'll have minus phi b of x from the first part, multiplying then here the x derivative of phi a, and phi a also depends only on x, so I can write as phi a prime of x. And that is my result, and that must equal then some constant. This is what we had concluded for our particular case. It's a constant with respect to x. Now, to determine the value of this constant, it's constant, right? So I can evaluate the constant anywhere I want, and it must be equal to its value there. So let's evaluate at x equals, say, positive infinity. Now, at x equals positive infinity, right, this current density, if I stick in positive infinity for x, because these are bound states, I know phi a and phi b have to decay exponentially because this is a bound state. They must decay exponentially, so as I go out to infinity, I'm going to get 0 in both cases. And so I conclude that the current density, well, it's a constant, and at infinity it's 0. So it's 0 because it's constant everywhere. So this factor is always 0. And that gives me a pretty simple equation then relating phi a and phi b. I might even be able to solve that equation. So let's write down that equation. If this gives me 0, these two terms must be equal. And then I can kind of get all the terms of one type on each side of my equation, and I can do that by dividing by phi a and phi b. So let's take this first term. When I divide by phi a times phi b, the result is just phi b prime of x divided by phi b of x, right? And then this must equal